All right, for today's explainer, we're going to dive into a pretty incredible piece of science. It's something that powers so much of our modern world, but it's totally invisible. We're talking about vapor deposition. So let me ask you a quick question. What do your smartphone screen, the solar panels you see everywhere, and even a simple mirror have in common? I mean, they seem totally different, right? But believe it or not, they all share this one secret foundational technology. And here's the answer. Every single one of them relies on these invisible, ultra-thin coatings. And these coatings are created by, you guessed it, vapor deposition. It's kind of the unsung hero here. It's what gives your phone screen its toughness, makes solar panels work so well, and gives mirrors that perfect reflection. It's a technology that's literally everywhere you look, yet you can't see it at all. So here's what we're going to cover. We'll look at the art of these thin films, how they're built atom by atom, check out the difference between chemical and physical methods, peek into the hybrid future, and finally, wrap up with why mastering this stuff at the nanoscale is such a big deal. Okay, let's jump right in. We're going to start with the art of these thin films. And you have to understand, we're not just, painting something on a surface. We're literally constructing a brand new layer of material, one single atom at a time. It's just precision engineering on a scale that's almost impossible to imagine. So what exactly is vapor deposition? Well, at its core, it's a process where you take some solid material, turn it into a gas, a vapor, and then you let all those individual atoms or molecules just settle and condense onto a surface. That surface is called a substrate. And what you get in the end is this perfectly smooth, solid, super thin film. All right, so how does this film actually get built? It doesn't just appear out of nowhere. It actually follows a really specific four-step blueprint. Let's break down how it goes from just a few atoms to a complete layer. So it all happens in 4 key stages. First up is nucleation. Think of this like the first few seeds being planted. Tiny, stable clusters of atoms just starting to form on the surface. Then comes island growth, where those little seeds grow bigger and bigger into, islands. After that, you get coalescence. This is where the islands start to touch and merge together. And finally, everything connects, forming a single, solid, continuous film. Simple as that. Now, the really cool part is that scientists aren't just winging it. They have all these control levers they can pull to get exactly the film they want. They can tweak things like the temperature of the surface, the pressure and the flow of the vapor, and even the chemistry and, the roughness of the substrate itself. And why does all that control matter so much? Well, because it determines everything about the final film. We're talking density, how well it sticks, its texture, even its optical properties, like whether it's shiny or anti-glare. Every single one of those things is engineered just by carefully tuning those levers. Okay, so we get how the film grows, but where does the vapor actually come from? That question leads us to the 2 main toolkits scientists use for this: chemical methods versus physical methods. Let's put them side by side. First, you've got chemical vapor deposition, or CVD. Here, gases actually have a chemical reaction right on a heated surface to create the film. It usually needs higher temperatures, and it's amazing for what we call conformal coatings. It can wrap perfectly around really complex shapes. Then you have physical vapor deposition, or PVD. This one is more direct. You physically vaporize a solid material and just let it condense. This can be done at lower temperatures, and you get these super dense, pure films. But the catch is, it's line of sight. The atoms can only land where they can see. So here's a really simple way to think about it. CVD is kind of like baking a layer on. You're using gases and heat to cause a chemical reaction that creates something new. PVD, on the other hand, is much more like spray painting with atoms. You're just physically blasting a material from a source onto a target. But of course, science never stands still, right? The lines between CVD and PVD are starting to get really blurry. We're now moving into the next generation of deposition, the future, and it's all about hybrid approaches. And this is where things get super cool. You have techniques like atomic layer deposition, ALD for short, which gives you the ultimate precision. I'm talking 1 atomic layer at a time. Insane. Then there's plasma-enhanced CVD, which uses plasma so you can do the whole chemical reaction thing, but at much lower temperatures. And of course, there are true hybrid systems that actually stick PVD and CVD into the same machine, letting us build these incredible complex multi-layer coatings. And really, that's the whole point. It's about combining the best of both worlds. You take the insane precision of one method and mix it with the speed and efficiency of another. And when you do that, you just open up this whole new universe of possibilities for designing materials. Okay, So let's tie this all together. We've seen the process, the tools, the future, but let's get down to it. Why does mastering all this stuff at the nanoscale actually matter? What's the big picture? It really all comes back to that very first step, being able to control how those first atoms land and start to grow. That is the absolute key. That control is what allows us to create an anti-glare coating on your phone, a super efficient layer on a solar panel, or that flawless finish on a mirror. It's the secret sauce behind so much modern tech. At the end of the day, this is all about engineering materials at the nanoscale. That precision gives us the power to build things with a kind of uniformity and performance that you could just never, ever get with regular bulk materials. We are literally telling the atoms where to go to get the exact properties we need. Which, of course, leaves us with one heck of a question to think about. If we can truly build brand new materials atom by atom from the ground up, what's next? What should we be building? What problems could we solve if we could design the perfect material for any job? The possibilities are pretty mind-boggling.